Welcome, folks, to Meeting C++ 2023. My name's Mike, and I'm going to give you an introduction to C++ containers. And this is really going to be about knowing your data structures or giving you an overview of what's important and, again, how to use what's available to you in the C++ standard template library. So here's my information if you want to reach out or get in contact or see some of my other resources, and I'll talk about these things in a moment as well. But just so we go ahead and get started, again, here's the abstract that hopefully brought you to this talk or enticed you to watch later on. Again, our goal today is to get an overview of what's available in containers in C++ 2023 and have an idea, again, of where to start and when to use each of these data structures. So the code's going to be available for this talk if you'd like to grab it later or play around with it. I've tried to give commented samples as well, so feel free to dig into what I have uploaded there. Otherwise, a little bit about me. I'm an associate teaching professor currently at Northeastern University in the US in Boston, and that's my primary role. And on occasion, I do consulting on computer graphics projects and occasional training in C++. You can find me on YouTube. You can dig around my website or my courses page as well, where I have additional trainings available. Now, today we're going to be looking at the standard template library and the containers, and there's many different containers. In fact, I'm going to fit in most of them in this presentation to again give you a high-level overview. But if you'd like to see specific use cases and more, again, those are highlighted in some of the videos that you can see here, programming from literally an empty source file to actually running some experiments and so on. So feel free to dive in there if you don't find everything. Otherwise, you can find this talk, again, as a general overview, or many other wonderful Meeting C++ 2023 talks where you'll learn more about containers and a standard library and so on. So let's go ahead and just start from the beginning, though, for this talk here. And I want to just start talking about data. And what do I mean by data or data is this idea of what a machine's role is when we are programming. And some of you might know what this machine is here on the right. This is a prototype or an early example that somebody built of a Turing machine created by Alan Turing. And my purpose of putting this here is just to inform you or remind you what computers' jobs are, to just take data in, perform some operation, and give you potentially a new result and transform that data out. That's it. It's kind of comforting to know that that's all computers are doing at the end of the day, because then we can think about how we approach this process and improve it over time. But in order for us to pragmatically write software that's going to be useful, we probably want some higher level abstractions so that we're not just looking one instruction or maybe one byte at a time and trying to figure out what to do with it. So we have some fundamental data structures as one of the ways for us to help abstract this process and help us think about how we're transforming and storing data and so on. And that's the purpose of a data structure, right? This idea that we're able to store and organize data, similar to an analogy of how you might store data on a bookshelf or in a drawer somewhere. Computers are going to try to do the same thing with some high-level abstractions. And some of these are given to us in libraries or maybe even built into the programming language. So that's the idea, that we want some ways to store and organize data, and that's why you're here to learn about various containers that we have for data available in C++. So fundamentally, to sort of start building up this analogy and understand what we've got here, in C++ we have built-in arrays. So again, most of you are going to be familiar with this idea of creating a raw array of some amount of memory here, and you can allocate this array on the heap here. So here's a visualization of where an array of 9 integers might fall into memory. Arrays, again, being a sequential chunk of memory, all of the same data type. Okay, so that's the idea, and we can index into this memory. But again, this is our first way of sort of organizing data in this nice sequential structure. And we can allocate this statically. So there's a few examples on the right here just showing on the stack, allocating exactly 9 elements, for example, in this fixed size array. Or below here, we can dynamically allocate memory if we need more. So in the instance that we need to make a huge allocation, again, that's an option to do that on the heap by requesting memory from the operating system from new here and doing a large allocation. So this is perfectly feasible and legal here for us to do. But we do have to be a little bit careful here when I do this allocation or request for memory from the operating system here with new here, because I need to make sure that I delete this memory here. And this is effectively us doing some manual memory management. And that if I'm requesting, well, what is this, 1 million integers here, that I'm actually freeing that memory when I'm done with it. Of course, these things become more serious when you have a loop or a long-running program to make sure that you're not leaking resources. But regardless, this shows us how we can allocate some large contiguous sequence of data and even pick the size at runtime. And again, that's the point of having statically allocated versus dynamically allocated memory here, with this example shown with new. So that's the difference here with how we're allocating memory. So fundamentally, beyond the built-in array structures that we also have what are known as linked data structures. So this is a way to sort of expand or contract data structure, but we're really just thinking about it as sort of a fixed size unit. So maybe one node or one link at a time here. And in C++, we have built into the language pointers, which is one of the mechanisms where I can sort of link or point to the next node in a sequence of data. I'll show you an illustration of that in a moment here, just again so we have the full visual picture in our mind here of how these data structures work. And these linked data structures can be used to create, well, individual lists as shown here, or trees that branch left or right, or maybe they have multiple links like in a graph. So again, very powerful way to store, organize our data, which is the point of data structures. So again, usually when we're thinking about a linked data structure, we're thinking about some sort of node here. So I'll draw your attention to the right side of the screen here, where I have this struct here with a node, and I have some data here and a pointer to the next node that I'm linked to. So that's illustrated roughly with this diagram here, where I've got my data, an integer or perhaps some other type, and the node pointing to the next struct that consists of some data and the next node, until we maybe run into a null pointer or some sentinel value that tells us, hey, we're going to terminate. We have no more data in this link of structures. Now with linked data structures, thinking about this maybe from a memory standpoint, we don't really know or have a guarantee that this memory is going to be contiguous. Maybe we have some idea, but again, we don't know if we're allocating these nodes with, say, new, for instance, that they're going to be one after another. And that leads to other important discussions when it comes to performance and some ideas we'll touch on later. But hopefully you understand this fundamental idea here of how we can add nodes together quite nicely here in this structure here. And this is a link structure or maybe some sort of list, which is often implemented in this manner. So we have these building blocks, these fundamental building blocks for organizing our data. Built-in arrays, maybe they're static, maybe they're on the heap, so we can do large allocations, and linked data structures where we can connect through pointers. And we should also consider that I can combine those two ideas to this third picture on the bottom right to have linked structures of arrays. Or we could even flip that around and have structures, for instance, lists of arrays, for instance. So however you want to think about it, just these simple abstractions allow us to build more intricate and interesting data structures already. So that's the general idea with our building blocks. Now, of course, as I've already alluded to, depending on if we have a linked or a contiguous data structure, this can lead to many trade-offs. And some of you have learned about various data structures. Again, this might be review for you and you just want to see the containers. But for those who haven't, again, how we organize our data really impacts the performance. Again, imagine going to a library, for instance, with one huge bookshelf, one book after the other, or a library that has things organized in sections, maybe categorized. That affects how long it takes you to find what you're looking for. Same thing with data structures, and oftentimes we categorize them with the access time for retrieving something, the search time to find something, and then other things like how long does it take to add a new piece of data, or in the library analogy, a new book to the library, such that we can have room for it in that library, or otherwise remove something. So again, these are some of the trade-offs that we want to consider. And along with this, some other things or factors we think about with our data structures are whether they're fixed or resizable. Maybe they're just allocated one time. So again, there's many different trade-offs here. Sometimes even just the ease of use of a data structure. So you can observe this, and you can visit this website here if you'd like to take a look at or refresh a little bit when it comes to complexity of your data structures. But let's go ahead and proceed here. Now, here's the good news for us. It's that all that knowledge you've learned, or maybe are learning right now about different data structures, well, that's going to come in handy because we can just literally choose the right container off the shelf for us. Because C++ comes powered with several data structures, or containers as they're going to be called, for us to use. So let's go ahead and take a look at the standard template library here, getting a little bit of a brief history, and then we'll keep working towards containers here. But everybody should know at least a little bit about the history of the STL that was proposed by Alexander Stepanov around 1993, and then sort of incorporated or released in 94 and officially adopted in 98. But this idea that we should have some built-in data structures and that they should be generic, meaning I can work with integers or a custom type that I make, strings, etc. So that's the idea and sort of the power of this. And then I should also be able to use some of those containers and data structures with things like algorithms and so on. So generally speaking, we have the standard template library available with many different compilers from many different compiler vendors, and it's supported fairly well on pretty much every platform where you can find C++. So again, here's a view, a high-level view of the standard library here. And you can notice we have lots of tools available. Again, today we're going to be focusing on something known as containers, our data structures, which we've begun talking about. And we're going to be talking about specifically the ones filed under the containers library section. There's other things like pairs, tuples, strings, bit sets, val arrays, and so on that are available and interesting to perhaps know about that are also containers or data structures. But again, we're going to focus on the core containers. So here's our overview. Here's where we are with all of our containers and various libraries. And as mentioned, here's where we're going to focus, just this piece today. So within the containers library, there's actually 4 main categories of our containers that we want to take a look at here. So I've got sequence containers, associative containers, container adapters, and unordered associative containers. And this is roughly how we categorize them in C++. And this is probably similar to how you might think about them in terms of the data structures. Sequence, things that are sequential. Associative, maybe some sort of key or value relationship there. Unordered, well, specifically telling you that they're not in any order. And adapters is kind of a funny one, but we're going to think about these as an interface to using some of our data structures. Okay, so let's go ahead and proceed. And again, with C++ containers here. And again, the motivation here for using these versus, say, building your own data structures is one, because you get these powerful, already built data structures available with your C++ compiler. So again, they're generic in the sense that I can just have, for instance, in this vector, which is one of the containers we'll talk about, a collection of integers. Or I can create my own user-defined type here, UDT, and also use that. It's just as simple as populating the parameterized template here. And that's really it. And of course, you can take advantage of the CTAD, class template argument deduction, to just populate data if you're not exactly sure. And C++ will usually do a pretty good job of figuring it out, though I recommend usually putting in the type here. So anyways, with containers, they're generic, meaning you can use them with, well, any data type that you come up with. And there's also some interesting ideas with having generic data structures here. So this is a little bit of an aside, but if you're really interested in templates or playing around with this stuff, once you learn about a container like vector, you might also learn that, hey, maybe a list is a better way to solve this problem. And effectively, you can just swap one for the other. Whether that's for ease of use or safety or performance or whatever reason, you can actually just effectively swap these out. So here's just a little illustration here of something known as an alias template, where you can pass in the data type and the container and just replace with my type here. So you'll see that that's been replaced with the previous example there. Just some fun stuff you can play around with. But again, motivation for the containers. Now, secondly, the containers are well tested, meaning that, again, the result of decades of engineering and iteration on these containers means you'll at least find somebody who probably knows how to solve the problem on a web forum or on your team because again, the STL has been around for a really long time. And again, is typically well tested by hundreds of thousands, say, of C++ developers. And the third and final point, again, because they're part of the standard template library, they work well with things like the algorithms and iterators that are provided with C++. So you can kind of see that iterators are the glue between where I'm storing my data and how I'm accessing it and what I want to actually do with that data on the algorithm side of things. And here's just a small example showing you how to filter some data that's been generated. So again, this is the idea with containers. You can pause the video and digest this example if you want, but we can see that everything's being touched on here. I've got a container with a vector. I've got some algorithms here for generating data or otherwise copying and filtering that data, and then some iterators telling me how I want to move through that data and access it. Okay, so that's the idea there. All right, so with that introduction here, let's actually get to talking about the containers here. Now that we're really excited here and we can think about our sequence containers, well, here they are: array, vector, dec, forward list, and list. So what are sequence containers first and foremost? Because this is how you'll see them categorized. This is how you can talk about them or search for them on the internet if you need extra information. But again, these are containers where you're thinking about accessing each element one after the other, meaning that you would say next item or plus plus to literally increment, pre or post increment to move an iterator to the next element, or if you have random access, just 0, 1, 2, thinking about the actual index. So you can see that they're all laid out in a line here, as opposed to a tree or a graph type of data structure here. And you'll also observe that this means that we have some that are contiguous and some that are linked data structures, as we talked about at the start. So some are backed with an array and some with a list. So array, vector, dec, list, and forward list are the 5 sequence containers that we're going to take a look at here. So let's go ahead and start with array. I'm going to provide for all of our containers here a quick snapshot so that we can see what's available. And you can go to CPP reference or your favorite other documentation source to see these elements here. But what I see here with an array, again, it's a generic data structure, meaning there's going to be a particular type, and we're going to actually set the size of an array at compile time. And again, an array here, std array. Here's the type, here's the number of elements that we'll have, and here they are. Okay, looks exactly or almost exactly like a built-in array that we talked about at the start of this talk. And this is something that's new since C++ 11, this idea of having a standard array data type. And again, functionally, it's exactly the same as a raw array. So it's going to be stack allocated, meaning we have this contiguous array or data structure. We can't resize it. If I say it's 5 elements, it's going to be 5 elements, as illustrated on line 23 here. But again, we use it just exactly like an array here. But we get some power with this abstraction here. And again, this is something that you might consider in your programming career as sort of interesting, that sometimes, even if you have a very primitive structure, you might want to add a little bit of abstraction for safety or improving your use case here. But we can see that we have member functions like .at versus just directly accessing the data. .at, for instance, will give us some bounds checking, and I'll throw an exception if we would perhaps say, hey, I want to access this element at index 5000 or something, beyond what we have allocated. So that's the idea here. Now there's several other useful member functions that are available. Again, you can take a look at some of these in the documentation or here for getting the first or the last element or the size. And size itself is actually a really nice one to have if you've ever worked with raw arrays, because sometimes you have to think about, was it stack or heap allocated? Well, here we always know it's going to be on the stack, and we can just see what the actual size is here. There's also a really other nice property of standard array. Because it is a container, we know its type. Now, what this means is when we pass arrays around in functions is they don't decay to pointers or any other weird sort of stuff. They are always standard arrays, and we always know their size. So again, arrays a nice abstraction. Now, looking at this from the container perspective here, arrays, again, are static. They're fixed at compile time. We have random access. And if we want to search them, we can sort of run our favorite searching algorithms, right? If it's not sorted, we need to look through everything to see if an element's there. If it is sorted, maybe you can run a binary search or perhaps some other algorithm on it. And a few other notes, as mentioned, again, we know our length. The interface is also, because we get to choose, similar to other data structures. So as we're going to talk about other data structures, or again, containers, the C++ way to talk about it, we'll see these .at, .front, and so on as member functions. So when I think about if I want to swap this actual container, maybe for something that does expand, that's a nice, an easier change to make. So in general, anywhere where you're using a raw array, you probably want to just go ahead and start using a standard array if you're using C++ 11 or beyond, which I would recommend anyways. Okay, so that's with an array. Let's talk about vector, which is perhaps one of the most popular data structures in C++. Again, we can see that it just takes in some sort of type here, and it's got this allocator parameter here. Now, usually we're happy with the default. That's what we're going to see 99% of the time, or more, perhaps for some of you. And that's what we're going to see in this presentation. But this is a hint that we are allocating memory at runtime so that this is an expanding data structure or an expanding container. Okay, and similarly, you'll see some of the member functions that we have available. Again, you're going to see lots of repeats, which is a good thing because we have a sort of common interface that we can use if we need to swap containers. Okay, so let's go ahead and take a look at vector here with some examples. And again, this is a dynamic array. That's probably a better name for it. So don't confuse it with a mathematical vector if that's what you're thinking about things. But the idea here is when I have a vector, I can actually push in elements to the back of the vector, and that's what's going to cause it to expand over time. Or I can also remove elements by popping them from the back, and then that will contract the data structure. Now, regardless, this remains a contiguous data structure. That's how things are laid out in memory here. But again, it can expand or contract, which is different from the array that we just talked about. So this is a, again, resizable container. So again, this is sort of a more accurate view or visualization of the vector data structure here, meaning that there's some pointer to memory that we've allocated on the heap. And then internally, we're also keeping track of the size and as well the capacity. The capacity is the maximum number of elements that we can store, and size is, well, how many elements that we've actually pushed back into our vector. So again, that's some bookkeeping that's done by the implementation of standard vector. So let's go ahead and just make sure we understand this before we move forward. So let's say that I go ahead and push back some value here, like the value 99, and some value is inserted here. Oops, and I'll actually update that to 5 just so that matches our visualization here. Let's be clear here. So if I rewind here for a second, I have 1, 2, 99, 1, and then I'm going to just push back 5, which adds to the end, because again, I said that this data structure could resize. Now, interestingly, if we flip back and forth between these slides here, you'll notice my vector has grown quite a bit, more than just pushing back the one integer 5. And that's because this has done what's called forcing an expansion or a reallocation of our vector. Now, again, what's going back, if we keep flipping back and forth, size, well, we've, of course, added one more element here. That's relatively clear. But our capacity has actually doubled here. Or really there's some factor here. Maybe it's 1.6 times larger, maybe it's twice as big. It doesn't really matter. It's sort of implementation defined here. But the point is, if I put something on in the vector, I'm likely to add something else later into the future. So oftentimes behind the scenes, the vector will actually double. It's kind of like when you go grocery shopping, usually you buy food for more than just that day. Right? You kind of decide, well, I'm going to need to eat in the future. So you buy a few more groceries or a bigger size jar of something. And that's the same idea with a vector, because you're likely to do some operation again, like add to it because it's expanding. So in this way, it makes it cheaper the next time we add an element because we can directly do that at index number 5, 6, 7 until we need another expansion. So that's the idea here. Now, of course, you might say, well, Mike, that was really wasteful. So what if I truly only need 5 elements? Maybe you've measured, maybe you know exactly what you need. Well, then you can always shrink your vector, and that'll make sure that you're given exactly or relatively close to whatever your actual size is, right? This capacity, it might choose a nice number like a power of 2 or something. Again, that's sort of implementation defined, but let's go ahead and say that we're going to reduce this capacity to exactly the number of elements we have, 5 in this case, and that again is more efficient if space is more important to you. So again, these types of things have been thought about, they've been implemented, and you don't really have to make sure you get all of your pointers right. It's probably a fun exercise to implement your own vector, but again, you know, it's nice to have these tested data structures. So what happens though if I want to insert 42 here, but this time at another index? I showed you pushback, but we do actually have an insert member function because, well, it'd be nice to be able to just arbitrarily insert data anywhere. So this is something where we have to think about our containers and just understand exactly how they work. For convenience and small programs, this is great, but again, at scale, we want to think about this. So let's insert 42 here. And what you're going to see has to happen is, well, I need to do that expansion again. I need to effectively duplicate my vector. And again, maybe that's by some specific factor. For the purpose of this visualization, let's just say it happens to add 1 element. And we have to copy 1 over to its index, 2 over to its next spot, 99 to the next spot, etc., so that we leave that spot where we want to insert available. And then we can construct or insert that object there. In this case, it's just an integer. And then we need to free the previous memory and then make sure that our internal pointer inside of the vector, which again, the standard library takes care of for us, points to the newly allocated memory where we've copied everything. So that's what's going on if we want to insert at an arbitrary position in a vector. So let's sort of compare and contrast this with what's going on with what we previously talked about. If I just want to push something back, I might have to have a reallocation and copy everything. But in the average case, most of the time I'm able to just put something in an empty position here, and that's great. But if I want to insert at an arbitrary position that's not, say, the very end, I'm going to have to copy that vector again and move everything in a new position here. So just something to consider with our usage of the vector data structure. So in this way, vectors are much more flexible than arrays. We have to be a little bit careful with our insertion operations on occasion. But again, this container is going to do the hard work for us because it's already been implemented and tested very well in the C++ standard library. But again, it's just useful to understand how this stuff works. And you can query capacity and size and so on to, again, understand what's going on when you're inserting elements here. Now, as an aside, of course, because C++ is a language that allows us to get a lot of performance out of our code, we do have a handy function known as reserve, which allows us to just say, hey, I think I'm going to need 6 elements from the start, and just reserve that capacity right away. And then you can do lots of insertions or pushbacks rather without much cost here. Okay, so there are some ways we can dig deeper, and I just want you to know about those. So when it comes to vectors, again, they're dynamic in their memory allocation. We can have random access, just like an array. And if we want to search, we might need to look through every element or maybe a binary search and so on. Now, the vector is typically our default container for performance and flexibility. So just keep that in mind as you're doing your development. Again, it depends on the problem you're trying to solve, but vectors usually the go-to. All right, and again, as mentioned, here were just the notes on the little optimizations and ways to get performance. Again, thinking about some of these operations like reserve or shrink to fit if memory is a premium. And again, that's the idea. Now, string, which we're not going to talk about, is effectively a vector that's handy for working with character types, but again, you might have a vector of bytes or something. So again, there's reasons to have these as separate data structures. Okay, so let's talk about the deck, which is something that you might not realize is being used a lot behind the scenes, but is an interesting data structure. And this is what's known as a double-ended queue. So you can see a visualization of it up here, meaning that we can grab the front elements and insert there, or the back of the queue and insert elements there as well. So that's the idea of what a deck is, or a double-ended queue. And it's interesting to note that they're not necessarily a data structure that's fully contiguous like the array or the vector. We are seeing that is a linked data structures here, and it is something that's a linked set of arrays or nodes. Okay, so that's the idea. So let me give you a little bit more of an honest picture of what a deck looks like on an implementation. Again, you could implement this several different ways, but most likely what it's going to look like is your deck data structure is going to have some sort of mapping. So if you want the 0th element, you're going to go to sort of the 0th chunk that has something and map your way over to maybe some tinier array of maybe 2 or 4 or whatever the implementation decides is reasonable in those elements here. So in this way, we have this mapping that's very interesting. So what does this mean for us as far as how a deck works? Well, observe that we have these question marks, which indicate empty. We can actually insert at the front of the deck relatively quickly and the back of the deck. So this almost solves one of the problems that we saw that was interesting with the vector, where if I did insert at position 0, I had to do this huge copy. With the deck, that's not so much of an issue because we can just insert an element at the very front or the very back with much less expense without having to copy the entire data structure. We just have to update this. I'm calling this a map here, but it might itself be a vector that points us to the right small little chunk of data. So that's the idea of a deck. So we can see how decks use the interface, however, is extending upon what we could do with the vector. So again, we'll see familiar member functions like push back, but we've also got this push front here, which is a operation that we could do in constant time. Now I will tell you with the deck, in the middle of the deck, we still have to be a little bit careful with our insertions, but at the front and the back, we can do quick insertions. So again, it's a resizing data structure. We get the random access that we enjoyed previously, and this search times stay the same based off if it's unsorted or sorted. All right. So let's look at a linked data structure here, which is a list. Now, a list itself, again, is similar to the deck, but this time explicitly one element per one of those chunks here. And in fact, we don't need this additional, if I go back here, abstraction with the map here, because we have nodes that just directly point to the next node. So a list is usually implemented in C++ as a doubly linked list, meaning that you can insert quickly, because it's a list data structure, a new node here. So whether you're pushing back to the end or inserting, as long as you know exactly where you're inserting, maybe you have an iterator, you can insert to that location very quickly. Now, if you've got to traverse the list, that is going to cost you, say, O of 1 time, or O of n time, excuse me, because you do have to traverse the list. But in some cases, you have the pointer available and you can do quick insertions otherwise. So in that way, it makes it a relatively flexible data structure in how it can be used. And the other thing with lists, particularly standard lists, which is a doubly connected linked list, or doubly linked list, excuse me, is that we can access the first node and the last node very, very quickly, because we oftentimes have pointers available in the implementation that give us the front or the back of the list quickly. So that's the idea with our list. You can see a few different examples, and there's other interesting operations we can do with lists, as well as our other containers like splicing them and moving one part of the list to another list. So if you're doing these types of operations, those are quite nice. And there's also merge operations as well that are nice to use. So the list itself is an expanding, again, data structure. It's easy to create nodes and add other nodes on it. but we need to pay some cost if we need to traverse it, right? We don't have that random access like we had with the vector. Now, briefly, I'll add a new data structure as far as is added in C++11, which is known as a forward list. And you can see that this one's, well, a lot simpler in terms of how it's actually implemented. It's just got a link going one way. So again, it's still a sequence here, but we can only really add elements one at a time here. So we can do this quickly by just creating a new node at the front of the list, but we can't traverse forwards or backwards. So in this way, forward list is just a very space efficient implementation of a list and with less power. So it's a lightweight container that was added. This is just a simple singly linked list. So the performance characteristics are going to be the same. And it's going to be fast again if you have handles to each iterator that maybe you store or cache over time, but otherwise you're going to have to pay the cost of traversing the list. Okay, so with that said, we've gone through the sequence containers here, and I want to briefly talk about some of the gotchas with these containers. Now, in some ways, I'm just going to post this. I know it's a wall of text here, but there are a few things that are important with any of the containers and worth knowing now that we know how few of the containers work. Just considering when we're pushing back, our containers own the data. Okay, if you want to actually construct them sort of in place, there's an in place function for that, which might reduce copies. So again, you can revisit some of this stuff as performance becomes more important. For removing data, we do have to think about how this works a little bit. Now in C++20, we have erase and erase if, which makes things easier. But these data structures and containers want to work quickly. So when we remove something, sometimes there's little tricks to just move where the actual end iterator is. And then we can call erase, which will do the cleanup for us. So keep that in mind. Now, also be careful if you have other things like pointers within your data structures when removing. So that's just a note about that. And generally speaking, take advantage of the member functions where available. Okay, so some other common gotchas are this idea if you have other iterators, and I've mentioned this idea a few times saying, oh, this can be really performant if you have an iterator maybe somewhere in your data structure. And in fact, with lists, it's less of a problem, but I do want to highlight this problem that can occur with, say, vectors, for instance, if you have some data structure that's shared. And this idea that maybe you have some iterator pointing into a vector here at some position. And the idea is, let's go ahead and push back, say, element 7 here. And immediately you should recall that we are going to have to add another node at the end of this data structure. And that's going to force an expansion or a resize here of, say, 8 or whatever that new capacity is going to be. But our iterator is still pointing to the old memory where this vector, the internal data used to live here. So we say that that iterator is invalid now. So you do have to be careful if you're going to have an iterator that's going to last a long time and point into some data structure here. And that's what's known as iterator invalidation. Okay, now there's some other things that warrant probably their own talks on thread safety, but you can kind of read through the notes here and just understand that it's safe to read from a container with multiple threads. Generally speaking, right, we can have lots of threads reading from our containers of data. We can write to different locations as long as they're truly different and accessed, by one thread at a time. But if we're simultaneously writing to the same location in our container, well, you're going to need to figure out some sort of locking mechanism or way to do a safe access without getting a data race. So by default, there are some issues that we need to think about or some abstraction that you can add on these building blocks of the containers. All right, so here's also the C++ reference take on various data structures and some of their trade-offs as a review of what we've looked at. Okay, now let's briefly talk about some of the container adapters. I'm not going to have to spend too much time on these now that we're actually familiar with the sequence containers. But the idea is that these adapters sort of reduce or restrict how we are able to use some of the data structures. So that's what an adapter is. It's not something new that's implemented. Rather, it's something built on top of, say, a deck, a vector, or a list that restricts how it's working. And again, I'll leave some of this for a perhaps data structures course, but you've got a queue, for instance, a first in, first out data structure. First element that I push in will be the first element that gets popped out when I call the corresponding pop operation. So you could imagine that we could keep track of people in a grocery line, for instance, with both a list or a vector type, or a deck type, for instance. I mean, these could be different ways for implementing queues behind the scenes. And that's exactly what we get with a queue here. If we look at the data structure, the container by default is going to be a deck, right? That's something where we can quickly push and pop things off the front, and push things on the back very quickly. So a deck and a list actually are the two fundamental data structures or containers that we've looked at that we could use to implement a queue here. Vector actually wouldn't be a great choice because, again, removing from the front would be expensive and we'd have to shift things as we previously saw. So that's what a queue provides us. And again, if I go back, notice that this list is much smaller, right? It's restricting how we use things so that we abide by this behavior that we want. So that's actually a good thing that we have built in here. So these adapters themselves, I'll briefly cover as we'll want to move on to some other stuff here. But again, they're dynamic, right? Because the underlying data structure is a list or a deck, which can resize, okay? And we really have to think about, I mean, some of these operations don't make sense, like searching. That's not the interface that we actually want, right? We want this first in, first out behavior. So that's with a queue. With a stack, again, same idea, except it's last in, first out. And we have a top instead of a front operation, because that's usually how we think of or visualize a stack. And we don't necessarily want a stack and a queue to be so easily interchanged. Okay, so we want a little bit of difference between those interfaces. So if you try to use some of these template tricks or just swap all of your queues for a stack, you would want to think about it for a little bit. So I think that's a good thing that not all the names actually match up. I think that's a very important thing to think about when you're designing generic data structures and containers and so on. So this time you can actually use a vector though, just thinking about what it's doing. You're pushing things onto the back and able to remove from the back. That sort of makes sense that a stack could be used, okay? But you could also use a deck or a list as well. And basically the same performance characteristics as a queue. Now, interestingly, there are priority queues. Again, similar interface to a queue, but this time the elements are sorted in a way here. And you can see this visualization here from fluentcpp.com, which is very nice, showing that you have the highest priority element on the top, and then there's sort of this heap-like data structure behind the scenes that you could use to implement a priority queue. So again, a vector is actually going to be the default here. But you are going to have to provide a custom comparator so that we know what is the greatest element if you're not using a primitive or otherwise library C++ type. So what do I mean by that? Well, here's a tiny example of a priority queue where you're pushing in some numbers, 32, 33, 31. And if you pop them off, it should come off 33, 32, 31 in greatest order, descending downwards. But if you create your own type, which I've provided a link for a video of how to do that, then you need to have some sort of comparator passed as a second argument here for the template, so we know how to figure out which object is greater than or less than the others. So that's the idea. Okay, and finally in C++23, we get something known as a flat map. Now this is something that you might have available in your compiler, depending on if you're on the cutting edge at the time of this recording in 2023. And these are a new set of flat data structures. There's 4: flat map, flat set, flat multi-map, flat multi-set, and so on. But I'll go ahead and show you later on in this talk what a map is and what a unordered map is. But C++23, we add in a flat map. And this is a way to basically take a tree and flatten it so you get a contiguous or sequence, like the data structures or the containers that we've been talking about before, vector and array, for example, and be able to access the elements very, very quickly because they're contiguous in memory, which is a very good thing for performance. So these data structures, and I don't have an example for it quite yet here, So I'll actually remove that. But the idea is, because it's on the cutting edges, we can get better performance if we're just sequentially looking through these elements here. In order to understand this, I think we're going to have to look at map and unordered map, which is, well, what's coming up in this next section here. All right, so let's get to associative containers and unordered associative containers so we can understand what's going on with that flat map and just some other ways to look at our containers here. I'm going to talk about these two containers side by side, specifically focusing on set, map, unordered set, unordered map. And the other two we'll kind of understand, I can summarize in a sentence effectively. But the main thing to take away from these is that just observing the name, one is going to consist of data that's unordered. So again, you can think about a library with perhaps no ordering of the books, but we'll talk about a fast way, a smart librarian that can still access a book very quickly, versus associative containers, which are actually ordered. Okay, they don't have the word ordered in front of them, but the underlying data inside of the container is in fact ordered. So here's a visualization of each of them. And on the left side, I've got a standard set, which is one of our associative containers here. And that consists of a set of unique keys. So you won't see any duplicates here, 2, 5, 4, 7, 9, 8, and so on. And they're in fact sort of ordered if I look through this tree here, 2, 4, 5, 7, 8, 9, okay? Well, this actually looks like a binary tree, right? So I have some way to look at, if I'm looking for the value 5 to say, well, is it greater than or less than 7? It's less than. Is it greater than or less than 4? Then I move this direction, right? So this sort of binary tree is the underlying idea with these associative containers. Now on the right side in the unordered set, I've got a hash table here. So the way that this fundamentally works is you have a table here, and you have a special, what's known as a hash function that'll tell you where to look next. So if I feed in this value 5, for instance, I might pass it into a hash function that tells me which bucket or region to look in. And let's go ahead and say we have a simple hash function here that just mods the key by 4, because I have 4 buckets here, just as an example. And it tells me, okay, 5 mod 4 gives me a remainder of 1, so look in this bucket here, and that's all the other values that have that same property. And then I sort of just look through that small subset. So interestingly, what this allows us to do is get really fast lookup times for our keys here that we're looking for in this set here. In fact, both are pretty good. This is log-based search time here because we're doing this binary search. But this is on the average case, if we've got a good hash function, constant time, okay? Now, constant time, again, might be a few steps. And in fact, if we have a few elements that keep falling in the same bucket, that could be problematic. But that's the idea here. Now, that's the idea with a set. We just have the keys directly. But oftentimes, we might want the keys in some associated value. And that's what a map does. Again, think about a phone book, for instance. You put in, and you could think about it either way, whether you have someone's, usually their name as a key, and then the value would be their phone number, or you could actually have it the other way around, because the phone numbers might be unique, and then get that person's name. But that's the idea here, that now we have a node or some sort of struct here that has the key, which is what we're going to, well, in the case of our associative containers, sort by this key. So again, same sort of binary tree, dog, and then alphabetically cat would come before and pig would come after. So whether you're moving left or right in this tree is how that works. And then as you move through the keys, then you can grab the associated value. Okay, so there's some structure here, or perhaps a pair of key and value. Now the same idea of key and value pairs holds true here with the unordered map. But again, we run through a hash function, which is just a table, to hopefully give us constant time lookup. Now in this example over here on the right, I've given you an example where, well, all of our keys are lining up to the same bucket. So usually that's not so good. And you can actually look through unordered map in the interface and look at what the bucket size is, how many buckets you have, and calculate the load factor. And if you have too many things going in the same bucket, you want to sort of reorganize or think about that hash function. Again, you can check out some of my videos on how to figure that out from scratch, but again, this is the fundamental way that things work. Okay, so here we go. Again, just discussing that idea. Now, as an aside here, I'll give you the one sort of sentence description: multi-set, multi-map, and unordered, multi-set, unordered, multi-map. They don't really allow us anything super interesting in the sense of what I want to talk about today, other than that you can have multiple keys that are, that'll sort of get organized here. So that's the idea with those. All right, so let's go ahead and look at our associative containers, and then we'll look at the unordered versions here briefly of set and map. Again, set, all keys are unique and in sorted order, and you can kind of see the interface here. I'll show you with an example. But because behind the scenes we have some balanced tree, that means that we're getting logarithmic performance here. We've got to search through that tree. But on the plus side, these are sorted. So if I wanted to access all the elements, or again, look through a phone book, for instance, then as I add, lots and lots of entries, my actual access and search time is still just logarithmic versus linear in the time that we are adding elements. So that's very powerful for us. And we have that nice sorted behavior. Now for maps, we have, again, similar to set, but a key and a value pairing. So this allows us to not just have keys, right? We have associated values with them. So typically what this means, if I draw your attention to this example, is we'll have a pairing for our key and our value in the map. So we need to specify when we create a map the key, which in this case might be a string, and the value, also a string in this particular case. And you might also use like a using or something. Using key equals stood string, using value equals stood string, just to get these things sort of straightened in case you get confused on the ordering, but that's just a suggestion. But we can see how we have this new pair here, cat, that we can insert directly into our dictionary, which is another name you might know map by. Okay, so the unordered set and the unordered map are going to be largely similar, but these unordered data structures come to us in C++11, which is a new thing that was a welcomed addition here, so that we could get data structures that effectively give us, on average, constant time lookup here and constant time search. And that's based off of having a good hash function that can tell us directly in some table, well, where exactly am I grabbing an element from, okay? And these data structures, like many of the ones we've looked at previously, set, map, unordered map, they're all dynamic. We can expand and add entries into them. Okay, and then finally, the unordered map, as mentioned, again, a hash table data structure, very similar interface, but this time we want to store pairs of entries. And we can see, again, that this is basically a drop-in replacement for what we've done with the map, but this time with unordered map. So we're getting constant time on average, insertions, access, and search. It's only on occasion where we have to resize, perhaps if we add a lot of entries, that we will have some, as that load factor grows, some performance penalty. But again, there's various tricks where you can set your initial bucket size and so on with these containers. Okay, so some common gotchas before we just wrap this up is it's important to note that with the associative containers, you can just use .at to read and see if you've got some value. One thing that I've noticed with new programmers in my classes is the operator, when you try to access something, it's a read operation perhaps you might be attempting, but if that key doesn't exist, or that pair, in the case of a map, if it's a key and a value, it'll actually create it. So that's something you just have to keep in mind here. So I like using at for a read operation, and you might want to have some abstraction for like create or something if you want. Just up to you, but that's just something to keep in mind. Okay, so let's go ahead and wrap this up because we've looked at a lot of stuff here. I mean, we've done a full tour of the C++ container library effectively. There are some examples. Of course, you can pause as you need to look through some of the code here, but I hope that gives you an idea of some of the trade-offs, how these containers look behind the scenes. And again, choosing the right container is often something that can give you a big boost in your performance, or maybe just the ease in solving a problem, right? That's why some of the things like the container adapters actually exist. All right, folks, I'd like to thank the organizers of Meeting C++ for allowing me to give this talk, you for attending, and hopefully you got a nice introduction to C++ containers. And, you know, even if you had a little bit of knowledge, maybe you learned some other cool tips and tricks, or can point other colleagues who need a start here on containers to this talk. All right, folks, thanks for your time and attention. And again, thank you, Meeting C++ 2023, for having me here. I'll look forward to talking to you all soon in the discussions or in the comments or wherever this ends up posted. All right, take care, folks.